Hi everyone. In this video about the TCA cycle, we're going to discuss anaplerosis, which it means um, the making up of things that were intermediates in the TCA cycle that are limiting and low. So we have discussed the main point of the TCA cycle, which is to generate electrons in the form of NADH, a little bit here with on FADH, but another major output of the TCA cycle is our key intermediates shown here in every one of these blue arrows towards biosynthesis. Okay, and so, which means that some of these intermediates will be used up for other purposes unrelated to the TCA cycle itself for its running. And we also discussed that the one intermediate with the lowest abundance is oxaloacetate. Now, the low abundance of the intermediates is good overall. So, because if you run it on a cycle, for the purpose of getting 2 electrons, as it goes around. But if you use up, so you don't have to maintain the intermediates in very high levels for the cycle to run, but you still have to maintain them at because you use them. So if you don't use them, you maintain them at low levels. But if you use them for biosynthesis, then you have to make them up somehow, especially the one of the lowest abundance, which is the one we're going to talk about, oxaloacetate. So there is one reaction we're going to do in detail. That's pyruvate carboxylase. It's a key reaction that takes a glycolytic intermediate, pyruvate, and converts it into oxaloacetate directly. Okay, so let me. I think we need to go onto the whiteboard, and we'll share the whiteboard. All right, so this is what happens in this case. The pyruvate will be carboxylated. That all that needs. This is all that needs to happen, right? But the carboxylation is not trivial. Okay, CO2. If you think about it, it's a gas. So how are you going to find it? I mean, the form of CO2 we have in our cells is usually carbonate. Okay, like fizzy. I mean, the bubbles that we see in soda, pretty much. And it happens to be very inert. Actually, it's not very reactive. So how are you going to activate it in some way so that you facilitate the carbon-carbon formation? You're going to have a carbon-carbon bond that has to be formed between CO2 and something that attacks it. That's something the carbon. I mean, the something that will attack the CO2 will be another carbon. Okay. And that will be a carbanion. So again, we have a stabilization of the carbanion. I mean, that's another major task of any carboxylation reaction. So A, how do you activate a fairly inert compound such as CO2? And B, how do you stabilize the carbanion? These are the tasks here. All right, so first, let's take the first one first. The CO2 is going to be in the form of carbonate. It will be something like that. Okay, and for that, we have to spend ATP. So ATP, which I will write like this. Will be used. I mean, we will hydrolyze ATP so the reaction can take place. So this one. So this bond here. Okay. So we're going to have ATP hydrolysis. The gamma phosphate will be attacked by carbonate, and we're going to release ATP. So that got hydrolyzed, And what we're going to have here is phosphorylated carbonate. Sorry. See, let me get my phosphates all right. There you go. Okay, so now we got activated CO2 essentially. Okay, so this is our CO2, and that can become CO2 if you lose the phosphate. And you see now you got CO2. Now that's a tricky reaction. You don't want to do it just out in the open because CO2 is a gas, so it's just going to go away. So your substrate is gone now, the source of carbon for the carboxylation. So you have to keep it in place in the active site of the enzyme and use it exactly and at the time when you need it. So the purpose, I mean, the stabilization of keeping in place, let's say, the CO2 is now done by a cofactor of the enzyme, pyruvate carboxylase. So the cofactor is called biotin. It's a cofactor of many enzymes that do similar things. And that's an important function of biotin to keep in place the CO2. And we're going to see this mechanism again and again. So how does it look like? So the enzyme will be here. And really the form of the enzyme is more like it goes back and forth. The structure of biotin goes back and forth between these two forms. The cofactor enzyme here. And what will happen is this form will keep CO2 in place. Let's write this. And what do we have? Okay. So this satisfies, by the way, this is biotin again. This satisfies some requirements that we have listed for the reaction, for the carboxylation, any carboxylation to take place. We have activation of CO2. The source is carbonate, okay, and we have to activate it, and we spend ATP in this case. And then we have to keep the CO2 in place, and this is done with biotin. Now we're ready to carboxylase, but we still have something to do here, okay? So we have to have a carbanion on pyruvate. Pyruvate will look like this. Again, that's our glycolytic intermediate. And it actually goes back and forth. We're going to have a keto-enol tautomerization here. So somebody's going to pick up the proton, the general base, and we're going to have this happening. So keto, and we'll go back and forth with the enol. Okay. And now that, so at this point now, we'll be ready, as it is kept here in place, the CO2, with biotin. This, and now we're going to have biotin coming out, and we have CO2 ready to essentially be attacked. Okay. By the carbanion that is forming on pyruvate, and now we have, let's see what we have. We have carboxyl group. Another carboxyl group. Okay, let's make sure we got our carbons 1, 2, 3, 4. That's oxaloacetate. Okay, so that's the mechanism of pyruvate carboxylase, right? So stabilization of the carbanion, keeping CO2 in place, and activating the carbonate. So here, stabilization of the carbanion is here. I don't know where this arrow came from. It was that arrow. So stabilization of the carbanion, keeping CO2 in place with biotin. I erased it, but I will by accident. Stabilization of the carbanion with biotin here, there it is, and activation also of CO2 by ATP hydrolysis. Okay, so let me stop sharing this screen and we'll go back to our slides and share another screen. We're going to see the mechanism again here. So this is again pyruvate carboxylase. We just went through the whole reaction. It's an enzyme that makes carbon-carbon bonds. Again, for that to happen, it's really the reverse of decarboxylation. Stabilizing the carbanion is the same concern. We went through how all these things have to happen: activation of carbonate, stabilize the carbanion, and what's the source of CO2? In this case, it's carbonate. It has to be kept in place. This is again the same reaction that we did on the board. That's the activation, all these steps, the activation of carbonate. This is the biotin that keeps it in place for the reaction to happen. Stabilization of the carbanion with a keto-enol tautomerization that's happening on pyruvate. And that's the general enzymatic mechanism that we described to produce oxaloacetate shown here. Right? So this reaction is a key reaction. It replenishes. This is what anaplerosis means. It replenishes and makes up whatever is getting dangerously low in the TCA cycle, so that the TCA cycle can keep functioning. It's also a reaction that fixes carbon, right? Inorganic carbon. It gets introduced into an organic compound in the form of oxaloacetate here. The enzyme is important. It is allosterically activated by acetyl-CoA. Does that make sense? Well, when you have a lot of acetyl-CoA, maybe you want to take it down the TCA cycle. And if your TCA cycle is not functioning properly because it doesn't have enough intermediates, such as oxaloacetate, then yes, that's a good allosteric effector to make oxaloacetate so that the TCA cycle works, so you can use all this acetyl-CoA that you have accumulated. Another very important reaction that does the exact same thing, generating oxaloacetate, that is PepCK, PEP carboxylase. It is not found in animals. It is found in pathogens, or many microbes, including pathogens that attack us. Okay, so it's actually a drug target. If you want to hit a pathogen, you don't want to hit something that we also have, an enzyme that we also have. So this has been an important drug target because we don't have this particular enzyme. And so that's useful. That's one reason why I mention it. Also illustrates the significance of anaplerosis and making up what you need in terms of oxaloacetate levels. The other reason is that you can see the same principles, even though we don't start here with a pyruvate, we start with phosphoenol pyruvate. You can see the exact same requirements that we discussed earlier about pyruvate carboxylase. Here we start with PEP. We don't start with phosphoenol pyruvate. We don't start with pyruvate. Now, phosphoenol pyruvate is already a high energy compound, very high actually. We discussed this. It's even the delta G, it's much higher than even than ATP, quite a bit so. So the phosphate, the high energy phosphate on phosphoenol pyruvate is the source of activation of carbonate, right? So this is carbonate. That's the carbonate that's going to be incorporated. It will react with whatever remains of phosphoenol pyruvate to give you oxaloacetate. So here the phosphate is a high energy compound. Okay, it triggers formation of the carbanion, and the carbanion here will attack eventually, as we'll see in the next one, carbonate. But before that happens, okay, the carbonate has to be stabilized. So we have it picks up this phosphate, just like we saw before with ATP hydrolysis in the pyruvate carboxylase reaction. So we make phosphocarbonate, and we have this form now of diphosphorylated phosphoenol pyruvate, which is stabilized exactly as pyruvate was before in the ketoenol tautomerization. Okay, and that's the carbanion here, and which of course will attack the carbon on the CO2 on carbonate, release the phosphate, and there you go with oxaloacetate. So it's the same principle. We just start with a different compound, phosphoenol pyruvate. It's a 3-carbon unit, of course, but it's also high energy 3-carbon unit. So you don't have to invoke ATP here. You just use the high energy phosphate and phosphoenol pyruvate, and the same principles apply. All right, so we will stop at this point, and we will continue, with the next video to discuss some interesting reactions of the TCA cycle.